Bismillahir Rahmanir Rahim. Today we are going to talk about the projectile motion. So the projectile motion is that kind of motion in which a body is moving in space under the influence of the gravity. So the only force that is acting on the body is the gravitational force. For example, if I throw this tennis ball up in the air, so there is only one force that is downward, and we can easily, since this motion that it's going up and it's coming down, so this is the one-dimensional motion, so we can easily calculate the time that it takes to the highest point and it comes back, because the gravitational acceleration that we know is 9.8 meters per second, and if we know the initial velocity and the final velocity, so we can easily calculate this. But today we will discuss the situation in which the motion is not in 1D, but actually it's the 2D. For example, if I throw this ball like this under the influence of gravity, so today we discuss here projectile motion. Since the flight itself is in the XY direction, so it's not in a straight line or in a horizontal line, so the path will be in the both an X and Y plane here. So I will draw the path of the flight. So it will be like this. So this is the initial point and this is the final point of our projectile. So this is our y-axis here, and this is our x-axis. So this is the object, when the object starts its flight here, so it will have the initial velocity, which is we represent it with the v0 here. So this is our initial velocity, since if we want to solve this problem in the 2D, so what we have to do, we have to split the whole problem in the x components and also in the y component. Then it will be easy to solve this problem. So this is the initial velocity, which is v0 here, and then we can split this into its perpendicular component. So this is our Vx, and Vx is v0 x, and this is equal to v0 cos of alpha. So this angle here is alpha. Similarly, so this one is our the y component of the initial velocity. So this is, we can write it here. So this is our v0 y, so which is equal to v0 sine of alpha. So this is the initial velocity, and now here this is our origin. So this is our origin here, and this is our maximum distance. So this is our maximum distance. So the object will start its flight in the xy plane, and it will go to the maximum position. So our maximum position here, so we call it P. So this is our maximum position, and it comes back to the maximum distance that it will cover in the horizontal axis, and that is we call it x. So this distance here is the OS, and the maximum height, this is the maximum height from here to here is the maximum height that the object will reach in the y direction. So this one here, from here to here, is we call it height. So this point is the highest position, and this is in the y direction, and this S is the highest or the highest distance that it will cover in the x direction. And now what we see here, since this is in the influence of the gravity, so there will be a gravitational acceleration which will be downwards here. So this object, the object that is going in this direction here in the xy plane, and there is only one, that is minus g. Minus g means it's downward. So, and in the x direction, there will be no change in the velocity, because there is no acceleration. The acceleration is only in the x direction. So the only velocity, because we can see here, so the velocity, initial velocity is v naught here, so it will be decreasing with the time, and when the object reaches here, so the velocity in the y direction will become 0 at this point. But in the x direction, since there is no acceleration and the gravitational acceleration is only in the y direction, so the velocity in the x direction will remain at the same vx, so it will not change. So this one, in the velocity in the y direction, will be maximum here, then it will be 0 here, and it will be maximum again here. But the velocity in the x direction will be the same throughout the flight.
Now we will try to understand the projectile motion with this animation. As we just said, that there is only one force, the gravitational force, and this gravitational force is causing the gravitational acceleration, which is downward. So the yellow arrow that you see on your screen is representing the gravitational acceleration in y direction. And now we want to see what is actually happening to the velocity components in y direction and x direction. So the green arrows that you see on your screen are representing the velocity components in y direction and x direction. If you look at the velocity component in the y direction, in the beginning it's maximum and it's decreasing because of the gravitational acceleration, and when the object reaches to the maximum point, the y component is completely 0, so you can clearly see. And it's again increasing in the opposite direction. So direction is changed, and it hits the ground, the y component is again maximum. And now we want to concentrate on the x component of the velocity. And if we look at it, since there is no acceleration in the x direction, so the velocity's x component is constant throughout the flight.
And now we will write the equations of the motions that we derived in our previous lectures when we were talking about the velocities and acceleration, and we will use those equations of motion to explain this complicated system. So the equations, so 1D equations of motion. So equation of motion. Why 1D? Because we have split our the velocities in the x component and also in the y component. So we will use the one dimensional in the x direction and also in the y direction. So we have the velocity in the x direction, and we have the distance that is in x direction, and we have the velocities in the y direction, and also we have the distance that is covered in y direction, which is height, and in the y direction we also have the acceleration, which is the gravitational acceleration. So we will use the one-dimensional equations to explain this system. So first, the equations in the x direction. So we have the x t x naught plus v. So x direction here t, and then we have the velocity in x direction. So we have, which is v naught x. Since our acceleration is 0, so we will not write the at term, because in the x direction we do not have any acceleration. So plus 0, so we don't have to write the acceleration in y direction. And now we have the y t equals y naught plus y v naught y t plus 1 by 2 a t squared, a y t squared. So in this case we have the gravitational acceleration. So, and then we have the velocity in y direction. So we have the y velocity, so v naught in y direction and plus a t here. So we have the 4 equations. So this is 1, this is 2, this is 3, and this is the 4th equation. So these are the equations of motion that we derived in our previous lectures. So this is the x, means the distance that is covered by the object, and this is the initial position. So usually this initial position is 0, so we have this term here. So this is the v velocity. If we bring the t here, so this is the definition of velocity, which is the time rate of change of displacement. This term is usually 0. This is the initial position here. And the in the x direction, when we look at the velocity, since the velocity is not changing because there is no acceleration, so the velocity is equal to the initial velocity, and it will always be the same velocity. It will not change. In the ideal case, when we ignore all the drag forces, that there is no air, for example, the resistive forces because of the air. And in the y direction, we have the same equation here, but we have additional term here. This is the equation of motion. So this is, for example, the distance when we derived it in our previous lecture. So when we derived this in our previous lecture, so this was the s, and this is again the initial position. So this is usually 0. When in our case, for example, we took our origin is 0, so this term is again 0, and this is the normal equation of motion. And this here we have the gravitational acceleration here, and here on the y, on the velocity here, so we have again this additional term here, again acceleration. In this case we did not have it because there was no acceleration. So here we have the term for the acceleration as well. And now we will see at the time equals 0. So when the time is 0, so what is the distance? So at the time equals 0, we have the x naught is 0. So we have the x naught, this term is 0, then we have the definition of the distance here. So this term is 0, and then we have the x equals velocity multiplied by time, and the v naught x. So this is the initial velocity, which is v naught cos of theta, which is this one. So, and here at the time equals 0, time equals 0 means when we were at the beginning of our motion, so the time is 0, so we have the y naught here is also 0. So as we said that the y naught is 0, so this is again the equation of the motion for the distance that will be covered by the object. And the velocity here is v naught sine of theta, sine of, or we can say alpha. This is also alpha because we use the alpha here. So this is the v naught sine of alpha. And in the y direction, we have the additional term, which is because of the acceleration here. So we have the acceleration, which is minus g. And now we want to know what is the shape of this flight here. So if we take the equation for the y-axis here, which is the function of the time here, if we replace the time using the equation number 1 and 4, so we will get, so I will not derive it, but we will get y equals constant x minus again constant c x squared. So this is the equation for the parabola. So that's why the shape is the shape of the projectile, or the flight, the shape of the projectile is the parabola. So if you are taking the mathematics course, you will understand that this is the equation for the parabola. So this is the parabola here.
So to give you some idea what the parabola is, in mathematics we have different shapes that can be expressed mathematically. So first one is the circle, and the circle has a constant radius and the distance is constant from the center. And the second one is the ellipses, and the ellipses we have two centers, and then we have the parabola and the hyperbola, which can be seen on the screen.
And now, using these equations of motions that we have derived in our previous lectures, we want to know what is this maximum height from here to here, and what is the maximum distance that the object will cover during this flight. So the highest point, so highest so we have to find the equation from which we can easily calculate the highest point. So if we look at the velocity in the y direction here, so if you look at the velocity in the y direction here, so this is the highest point. So we know that the velocity at the highest point is 0. So initially we had the velocity, but because of this acceleration, downward acceleration, the velocity was decreasing with time, and when the object reaches here, the velocity was 0 in the y direction. In the y direction we had the velocity 0, and it's coming back here. So if we use the equation number 4 here, so this is the equation number 4, and then if we find out what is the time that it takes to reach the highest point, and then we can put this value here in this equation, and then we will get the highest point in the y direction. So this is the y means this is the distance in the y direction. So we have the Vy, the velocity is 0 at the highest point, so we have the velocity that is 0. So we know from this equation here, so we write this equation, so we have the V naught y, so this is the equation number 4. So this is the equation number 4. V naught, so this is plus a t in the y direction here. So what is V naught here? V naught is the V naught y in the y direction. We have the V naught sine theta, sine of alpha. V naught sine of alpha, and the acceleration here is the minus g. So we have the minus g, and then we have the time. So if we find out what is the time here using this equation, on this side we have 0. So from this one we can calculate that the velocity, the time that it takes to reach the highest point is the V naught sine of theta. So this is the sine of alpha, and then divided by g. So we can write here h. So this is the time that it takes to reach the highest point. So if we put this time, which is the time that it takes to reach the highest point, in this equation here in the y-axis, the distance that it will cover in the y direction, so we can then find out what is the highest point. This term here for us is 0, so we have to concentrate only on this one here. So the height equals, so we have the y here, and we have the v naught y, and this term, so we have the v naught y, we have t plus 1 by 2 a t squared. And now if we put this t here, the time that it takes to reach the highest point, so we can that will be our equation for the highest point. So we have the V naught, so we have this is the V naught sine of alpha, and we have this one we put the V naught sine of alpha again, so divided by g. So this is our t here, and then we have the minus 1 by 2 g. This is our gravitation, and then we again replace the t with this equation here. So we have the V naught sine of alpha divided by g. So this is the squared because we have a squared here. So what we see here, so we have the V naught sine multiplied by V naught sine alpha. So this is V naught sine alpha. So this is 1 minus half. So we can see here they are the same term. So 1 minus half. So we will get, so the highest point, so this is our highest position. So this is the V naught sine of alpha squared divided by 2g. So when we calculate this one here, so we reach this final equation here. So this is the highest point, highest distance in the y direction that the object will cover in the y direction. So if we look at this equation, so we have the highest point is directly proportional to the velocity, the initial velocity. So if the initial velocity is higher, it makes sense. It means the initial velocity is higher, so it will go to the higher point if the velocity is high. On the other hand, we have the gravitational acceleration in the denominator. It means that if the gravity is higher, the highest point will be low, because and if the gravity is low, for example, if we throw the same ball on the moon on which the gravity is 6 times smaller than that of the earth, so the highest point will be much higher on the moon. And similarly on the alpha here, so the alpha is also, if we have the, for example, 90 degrees, so if this one is here is the 90 degrees, so sine of 90 degree is 1, so we will have for the 90, if the alpha equals 90 degrees, then the h highest point will be V naught squared divided by 2g. So it means that will be the straight path going up, and it will be going down. So this is something that we have derived when we were talking about the acceleration and the velocities, and in our previous lectures. And now we want to know what is the maximum distance, this OS. So we have already calculated derived a formula for this maximum height, and now we want to know what is this maximum distance in the x direction. So how will we do it? So we know that if we split this is a symmetric system. If we split the system into two, so we know the time that the object will take to reach this highest point. So this is the highest point, will start from here and it will reach to this point, and it will take this much time. So we have already calculated. And if we look at it, so this is the symmetric shape. So it will take the same amount of time from here to here. So if we multiply this time with 2, so that will be the time that it will take from here to here. So we will do the same thing in our case. So for the maximum distance, so maximum distance means OS. So the time OS is equal to 2 multiplied by the time that it takes to reach the highest point, and that is equals 2 multiplied by V naught. We have the sine of alpha divided by g. So now we have the time that the object will take to reach from the O to the P, and we can use now the equation here in the y direction, in the x direction here, and we put the time in this case here, and the x naught, we said that it's 0 for in our case. So we have the V naught, which is the V naught x, which is V naught cos of theta, and we put the value for the time, so we will get the OS. So OS equals V naught, so V naught x t. So we have here, so V naught cos of cos of alpha. So this V naught is the cos of alpha, and we take this formula here, which is for the time here. So this is the time. So we have the 2, and then we have the V naught sine of alpha divided by G. So we know that the cos of alpha and the sine of alpha is equal to, so we have 2 V naught, we have 1 V naught, we have 2 V naught, so we have the V naught square, and then the cos of alpha and the sine of alpha here, and then we have the 2. So if we use this relation here, so we will get the sine of 2 alpha divided by G. So this is the maximum distance. And now if we look at this relation here, we can see here that the maximum distance that it covers in the x direction is directly proportional to the initial velocity squared. So we try to understand that y is here a square, y is a square here. So if we look at it, if we for example double the initial velocity, that it means that the time that it takes to reach the maximum position will be doubled. And as the time that it takes to reach the maximum position is doubled, the horizontal axis means if we double this one here, so this one, the Vx will also be doubled. So when it's doubled, first of all we have the time that it reaches to the maximum position is doubled, and we have the vertical velocity is doubled. So that's why we have a square here. Now again we have the gravitational acceleration in the denominator, so it makes sense if we have a low gravity, if we throw a ball here on the earth and on the moon, the distance that it will cover on the moon will be higher because the gravity on the moon is 6 times lower. And now we look at the it's alpha here. If we look at the alpha here, that means that we have the 2 alpha here. So 2 alpha means if we have 45 degrees angle, then this term will be 1. It means that for the 45 degrees angle, we will have the maximum distance because the sine of 90 is 1. But we have the 2 here, so we should have a 45 here in order to make it maximum distance. So if we throw something in the 45 degrees angle, with the 45 degrees angle, the maximum distance will be, so it will cover the maximum distance. As we increase the angle is higher than the if we increase the angle as we reach the 90 degrees, the cover, for example, if we throw it in the y direction, so the distance in the x direction will be lower.
Now with the help of this animation, we will try to see what is actually happening to the maximum height in the y direction and the maximum distance in x direction when we change the velocity, the initial velocity. So we reduce the initial velocity, so we can see that the maximum height is reduced and also the distance that is in the x direction. So we slowly gradually reduce the initial velocity. So you can see here on your screen now it's 16 meters per second. So as we decrease the initial velocity, the maximum height of the projectile in the y direction is reducing, and also the maximum distance which is in the x direction is reducing. So this is perfectly making sense, as we saw that the maximum height was directly proportional to the initial velocity, and the maximum distance in the equation that we just derived was also directly proportional to the initial velocity. In fact, it was the square of the initial velocity, and we can clearly see that in this animation, that whatever we discussed, that makes sense. Now we want to see what is actually happening to the maximum height and the distance when we change the angle. And we keep the initial velocity. So we don't change the initial velocity, but we change the angle. So we slowly increase the angle. So we can clearly see that as we increase the angle, the height of the maximum height is constantly increasing. As we reach the maximum angle, which is 90 degrees, the height is the maximum. And now we look at the maximum distance in the x direction. So as we increase the angle from 25, as we are going up, so the maximum distance in the x direction is also increasing. But as we reaches the 45 degrees that we just saw in when we calculated the equations for at the 45 degrees we have the maximum distance. As we go above the 45 degrees, the maximum distance is again reducing. And so at the 45 degrees angle we have the maximum distance, and below and above 45 degrees with the same initial velocity, the maximum distance is lower. When we are at the 45 degrees angle, the maximum distance is the maximum distance in the x direction is the highest. And similarly in the y direction, so the maximum height is at the higher angle. So in the highest one, the highest angle, highest distance in the y direction is the for the 90 degrees angle.
So now whatever we discussed or we derived, that was in the case when we consider the air drag, or we just ignore the air drag, there is no air, for example, then we will have these equations and we will have a very symmetric position, a symmetric path here. But if we have a air drag, if we consider the air drag in our flight here, so air drag means that we will have the additional force, which will be the force of the air drag, so drag force. So that means that if we consider the air, we will have additional acceleration in this direction. So that means if we will not have this symmetric shape here, but rather we will have something like this. Because the drag force is causing the acceleration in the x direction, and it's reducing the velocity in y direction. As we go here, the velocity in the x direction, if we look at this one, it will be reduced, it will be lower and lower, and finally it will be 0 here. And I will just demonstrate it here. So as we discussed, that if we ignore the air drag and we just ignore that we do not have any air, then we will have the projectile, the flight, or the shape of the flight will be perfect parabola, and that we discussed in our example. But if we have a drag force, means we will have the additional acceleration in the x direction, so we will not have a perfect shape, but rather we will have an asymmetric shape. So I have here a tennis ball, which is kind of a little bit heavier, and I have here a sponge here. So this tennis ball will feel less drag force because it's a little bit heavy, and it's also symmetric here. And here it's very light object here. It's extremely light, the sponge. If I throw, just look at the shape or the shape of the flight here in this case. So if I throw the tennis ball, so you can see here it was perfectly symmetric. But if I throw the sponge here, you see it's not symmetric. So this is the idea behind the drag forces. So whatever we discussed in our lecture today, that was whatever we discussed here, that in all the equations we just ignored the drag forces. But just to give you an idea that how will the flight be affected if we really include our drag forces here.
Now we will try to see the projectile motion with the air resistance and without the air resistance. So without the air resistance, we have only downward gravitational force, and with the resistive forces, we also have the drag force. So you can see on your screen on the x direction. That's why the shape is asymmetric, and the acceleration and the velocities are also changing now. So this is here you see the gravitational acceleration for the projectile motion with no air resistance, and now it is with the air resistance. So we can see that the acceleration, the yellow line is the acceleration. We have the acceleration also in the x direction. And now this is, you can see the acceleration and the forces in both direction and the total forces.